So, good morning to all of you. I'm Francesco Bianchi from Università Cattolica del Sacro Cuore of Milan, and today I'd like to present you the study made together with Lorenzo Mercury and Eti Roy, and its companion R package called cogarch.rm. Our study focuses on the continuous generalized autoregressive conditional heteroscedasticity model. So nowadays, when we want to analyze a time series, the mostly used financial model is the Garch model, defined as a return function and a variance function, where the variance function, V small n, is an autoregressive moving average process. Similarly, a continuous Garch model could be defined as a GT process whose dynamics is described by this equation number 2. In this case, the variance Vt is a continuous autoregressive moving average process driven by the discrete part of the quadratic variation of the Levy process L small t. So you can probably wonder why we should use this continuous model instead of the well-known Garch model. So the main advantages of this continuous alternative are similar to the Garch model, that it can handle the arch effect, that is to say the autocorrelation of square return, and it can handle also the EV tails, where in the case of the Garch model we should choose EV tail distribution for epsilon n, while in the case of continuous Garch model we should choose a distribution related to the Levy process LT. Moreover, the model presented today can handle high frequency data and works on irregular spaced grid. Think, for example, to bank holidays or weekends. So in this way, there is no need of approximation of missing values. So let's have a quick look to the analysis performed. We considered a market composed by different assets where XIT is the process that drives the dynamics of a given asset I. At this stage, we were more focused in showing that it's possible to use Cogarch model in portfolio selection. So we used the independent component analysis, ECA, for describing the dependent structure of element in XT. It was assumed that the vectors that we observe, xt, are a linear transformation of independent statistical signals, SIT, SPT. So, in so doing, we need only to model the univariate sequences SIT, SPT, since the dependent structure is captured by matrix A obtained as an output of the ECA algorithm. So, the allocation problem was simply a maximization of the expected gains minus a multiple of risk measures on portfolio loss, where lambda is the risk aversion coefficient and rho is an homogeneous risk measure. In this case, value to risk or expected shortfall. So the empirical analysis implemented considered two different data sets lasting from April 2010 to December 2015, obtained through the function coggetData. The first data set is composed by 100 members of the FTSE 100 index, while the second one is composed by 154 European hedge funds tracking the same London index. Then the analysis followed this structure. So there is a leader selection combining cluster analysis and league lag estimation using the function CogLeader, a portfolio weights estimation based on the ECA CogArch model previously presented using portfolio Cog function, and a portfolio out-of-sample performance, in this case a 6-month forecast using the forecast Cog function. In this slide we can see 3 graphs obtained using the function forecast Cog. We can see different risk measures. So the red lines are the variant risk, the blue lines are the expected shortfall, and in particular we can focus on the bottom graph, the bottom plot, with a lambda of 10, where the result obtained outperform the European hedge funds simply tracking the FTSE 100 index. So to sum up, here we can see all the different functions implemented, both for the univariate and for the multivariate analysis. So that's it. Thank you for your attention.
Thank you. Please join me in welcoming Eina Oka for her talk.
Thank you. Hello. So my name is Eina Oka, and I work for the Energy Authority that serves public utilities nationwide for providing trading and analytic services. And my particular focus is midterm portfolio management. And for this purpose, I build and run stochastic simulation models for wholesale energy and gas market. Utility portfolio could include multiple different components. So utilities may own coal or natural gas thermal units. They may own wind, solar, or hydro generations, and then also usually they serve loads. So in order to capture the risk of the portfolio, we have to capture the cash flow of all these components. And in order to do so, I have to run Monte Carlo simulation for underlying market, natural gas or power. The unfortunate thing about this is that all of the time series represented as boxes here exhibit different characteristics. So as a result, I have to employ multiple different methodologies in order to capture this system. But the one that I particularly would like to talk about today is the middle one, generation of power prices. And here, what is actually important is that diagram shows is that power prices are nonlinear functions of other variables like natural gas or loads. And then it also feeds into thermal dispatch simulation model. So this actually means that I have to capture almost all of the characteristics of the power prices. The characteristics could include autocorrelation, seasonal or weekly shapes. It's usually heteroscedastic, and in fact, volatility tend to have seasonal or weekly shapes as well. I have to capture the multivariate cross correlations and nonlinear dependency on other variables. Distribution tend to be not normal. They usually have fat tails, extreme peaks and drops, and they can be negative. While achieving all these characteristics, I would like to also achieve consistency with market expectations and also between different time granularities. So when I started, simulating all these things, I looked at all of the traditional, approaches. And most of the approach for Monte Carlo simulation tend to be in the form of some predictive component F, plus some error component. And both F and error here can be functions of other things. But either way, from my experience, I've found it difficult to capture error sometimes, depending on which time series I'm dealing with. So that's when I started experimenting more with particularly random forest. So the random forest itself aggregates a large number of trees in order to achieve point forecasting accuracy. However, if I apply this to each Monte Carlo iterations, I found that I get too low of a volatility. So I looked at each tree. But each tree encompassed too little of a predictability. So if I use each tree for each Monte Carlo iterations, it was giving me too high of a volatility. So the answer I came up with is pretty simple. I started calling a modified random forest or bunched random forest, but simply aggregate a selected number of trees for each Monte Carlo iteration. And by doing so, now I can achieve a reasonable volatility for each Monte Carlo iteration while achieving a very similar result to the original random forest as the entire Monte Carlo simulation. And the plot here shows that as I increase the number of trees to aggregate for each iteration, the volatility for the iteration comes down. And in this particular case, you can see that if I aggregate 3 trees for each iteration, I would achieve volatility somewhat similar to the historical. I'm not going to go into details in implementation, but it's actually pretty simple. Random forest, the CRAN package, does output individual tree outputs, so you can utilize that. So by deploying this bunched random forest methodology, I could achieve results that was reasonable. And I don't have time to go into each details, but there is one thing I would like to mention. So for many of the stochastic forecasting, I use pinball loss function. But pinball loss function or any other scoring tend to capture only one type of model performance. Then I wanted to achieve so many different time series characteristics. So I found out that really no good scoring exists, and so that's kind of when I started doing a lot of visual inspection for the validations. But then I found one really useful thing. So if you remember, this power price time series feeds into the thermal resource dispatch model. And the dispatch model itself is very sensitive to all of the time series characteristics. So I've found that looking at the result of the thermal dispatch model and applying some sort of a scoring was a lot better measure. That's it. We're looking for, Seattle office is looking for the intern. Thank you very much.
And please join me in welcoming Matteo, who's going to talk about operational risk stress testing. Thank you.
Hi, good afternoon, everyone. Thank you to the organizers for inviting me here. So my name is Matteo, and I work as a macro rates strategist at Goldman Sachs in London. But before doing that, I was working as a risk manager in Italy, and I was focusing on operational risks. So today I will talk about macro stress testing of operational risks. The motivation of my research, of the research that I'm presenting today, is that in 2016, the EBA, the European Banking Authority, launched EU-wide stress tests for systemic financial institutions, and for the first time they included operational risk among the risks to be tested. So together with market risk, credit risk, liquidity risk, etc., they also included operational risk and conduct risks in particular. So we needed a model to basically forecast the response to macroeconomic shocks of an operational loss time series. So the general framework of what I'm presenting today is that we have some historical operational loss data that can be the frequency or the severity of the operational losses of financial institutions. Then we have a set of macroeconomic variables provided by the regulators, and then we have the macro stress test scenarios provided by the regulators. What we are trying to do is to measure the expected value of the operational loss time series according to the realization of a macro shock in the economic environment. After having looked to several models, I came up with a short list of 3 approaches. 2 of them belongs to the machine learning literature and are multivariate adaptive regression splines and the artificial neural network models. And the third one instead belongs to the econometric literature, and it is an error correction model. Just to give you a brief summary of the models, so the multivariate adaptive regression splines can be thought as a generalization of piecewise linear regression models, where basically the Mars algorithm is able to identify the relevant nodes and the relevant regressors automatically, and it also handles nonlinear relations and interactions among the variables. So Mars models are available in R under the ART package, because Mars, the term Mars is trademarked by Sulfur Solutions, so they are provided under different names. The artificial neural networks, as you know, they can be quite complex. I try to keep this as simple as possible. So I used a network with a single hidden layer, and I've tried to optimize the forecasting performances of the model by changing the number of neurons or by choosing a particular activation functions for the neurons in the hidden layer. Error correction models instead are models used by economists, and basically, this model is quite interesting because it allows you to simultaneously model the short-term dynamic and the long-term dynamics of a time series simultaneously, as I said. So basically, we kind of first estimate some long-term trend or common trend among the variables, and then we study the reconvergence to this long-term trend by looking at deviations around this long-term trend driven by the short-term dynamic. The data, as I said, have been collected from the institution in which I was working at the time, and the macroeconomic data were collected by looking basically at the requirements of the regulators. In terms of outcomes, for each of these 3 models, I've tested several different specifications. We have linear and non-linear predictors. For the Mars models, we have different degrees of interactions among the variables, and I also tested a bagging algorithm applied to the standard estimation of a Mars model, and this allows you to stabilize the forecast or try to avoid the overfitting problems that may arise in machine learning models. And then for this model, I've used cross-validation to identify which specification is better in terms of out-of-sample forecasting. With the neural networks, I did basically the same. Linear or non-linear networks, and I looked for the optimal numbers of units in the hidden layer to optimize the forecasting accuracy. This is just an example of one of the network I fitted, and then I tested for the out-of-sample root mean square error, and I tried to find the optimal model structure. The error correction models are estimated in differences, so basically in growth terms. These are time series models, so basically we have the past observations of the dependent variable centers in the right-hand side of the equation as well. We have to check for some characteristics of the time series, such as the stationarity or the non-stationarity, the existence of co-integration, and so on. So once I've identified for each of these models the best out-of-sample forecasting tool, then I was able to apply the stress test exercises. So basically I input the macro scenarios provided by the regulators, and I got some forecast out of sample or some simulation, let's say. I'm quite happy that the forecast of the different models, these models are very different from each other, but the forecasts are quite comparable to each other, so the shape we are getting are quite comparable, according also to different macro scenarios. So this is one of the scenarios that the regulators provided. This is another one in which the macro shock was much stronger. But in both cases, and also in other scenarios that we tested, the results were pretty comparable. Let's say that cross-validation was quite useful in understanding which specification is the best in out-of-sample forecasting, because actually all models can, according to this analysis, can be used. So at the end, I found out that bagged Mars with two degrees of interaction and non-linear predictors are the best in terms of out-of-sample forecasting, and that's it. This was the results that we were looking for replying to the regulators. Thank you very much.
And please join me in welcoming Thomas for our second stress testing presentation.
I'm already stressed. Right. My name is Thomas Zakrzewski. I work for S&P Global Market Intelligence in a division of the risk services. I have about 14 slides. If the fuse goes off, I will take all the questions offline. So I will be talking today about how we use the R for the regulatory stress testing modeling. So let's go back to the 2008 when we had the financial crisis, and majority of those issues that came up, but then was the asset securitization of leveraging by banks. Basically, their capital structure was not withholding the stress, and basically the financial system almost collapsed, and Federal Reserve's banks basically came up with the help and infused massive amount of liquidity to the markets just to have the money move again between the variety of entities. As a response to this event, there were created basically two regulatory requirements. One of the requirements, which is basically nicknamed DFAST, which is the Dodd-Frank Act Supervisory Stress Testing, and the other one was Comprehensive Capital Analysis and Review, CCAR. They both actually cover pretty much the same thing. The difference is basically just the size of the banks in a portfolio of the loans that they hold. So DFAST is up to $50 billion of the assets, and anything above was the CCAR. Now, both programs assess whether there is an appropriate capital structure for each bank, and also the Federal Reserve provides hypothetical scenarios for baseline adverse and severely adverse with microeconomics factors, and those actually are tested, is supposed to be tested in those models by all the banks. Now, we use R, and why we use R? Well, first of all, this project was conducted together with the students, which I will speak about this in a second. But R is the package which is the open source, right? I mean, this is a statistical tool, it's open source, so we like the transparency, the feds like the transparency, the banks like transparency. So it's nothing proprietary about the R, everybody actually can look at that. How is it implemented? So that's why the R has been chosen. Who we are, S&P Global Market Intelligence, we have the broad data for market intelligence, the risk services, we provide the models and the tools to assess the credit risk and the credit risk management for the professionals who deal directly. We work with the educational institutions all the time, and one of that institutions that we work on an every year is the Columbia University, and that model was actually created, there was many models actually, was created during the Capstone project with the Columbia University. We follow the data science procedure. So as every data scientist has to follow that, this is basically definition of the problem, scope, exploratory data analysis, data transformation, regression modeling analysis, model fine-tuning with the business, and this is the iterative process until we choose parsimonious and the best model. Now, the data description, okay, these are the interesting part comes here, okay, because the dependent variables actually came from the banks itself, and they came as the loans, and we have to basically calculate the proxies. And independent variables, there was a macroeconomic data from the reserve, from the Federal Reserve, and those are historical, and plus those three scenarios that goes forward at 3 years. All right, so these are the 15 type of loans that each bank actually reports in a call data, and we use this basically to calculate the proxies, which is the default rate, loss rate, growth rate, and PPNR, which is basically additional net interest income, non-interest expense, and non-interest income. And we choose the ARIMA, and there was a variety of different steps how we come up with the ARIMA, right? I mean, we always start with a linear regression. These are the most simple ones. Students love that because they're the most simple for them to understand. We also use the linear regression models for for detection of which variables actually are important, which one we should use it. And also the lasso regression and the shrinkage models like a lasso and a ridge also being used to further actually detect which variables we should use in a model. Here's the interesting, for the microeconomics variables, we use basically the subject matter experts, because as you notice right here, for example, nominal GDP and the real GDP and the CPI, okay, those are causing like various inflection, variance inflection factor is just that goes up to the roof. So it's not even in a single digit high of above 3, okay, up to the 10, but even it's just like a 20, 30, and a 50 sometimes. So you have to make sure that to eliminate multicollinearity, you have to look at that from the business perspective and just to see which one you have to remove. And these are the decomposition of the RIMA. You have the data seasonality trend. On the right-hand side, you basically have the whole schematic. These are the results, okay, for the multifamily loans. This is multifamily loans LR for the loss rate. This is the interesting one because we find out actually by the Elgin banks actually that it's not autocorrelated terms. So, but the package actually is very nice. So it's just a, creates basically all the components that we should use. The conclusion, as Sir George Box said, the all models are wrong, right? But some are useful. This actually becomes a useful model, and we'll continue to actually work with the Columbia students, and hopefully we'll roll this out to many banks as the one of the stress tests. Thank you.
So our next speaker is Andy Tang from one of our sponsors, William Blair. I think he's really up here though because Peter Carl didn't want to speak this year. But thank you, Andy. It's good to see you.
Thanks so much. Thank you. So today's topic is about structure, and it's the structure for covariance matrix. And we use covariance matrix for another purpose, like risk management or portfolio construction, like equal risk contribution or risk parity portfolio. But we may not spend enough time to think about the underlying structure of the covariance matrix. And today I'm going to talk about some of the different methods to estimate a covariance matrix and the underlying structure of each model, and to compare the forecast accuracy for them. Typically, we have two types of methods. One is fully unstructured, and the second one will be fully structured. For the unstructured one, it's very simple. The stock return follows some distribution, and the covariance matrix is estimated from the return themselves. These models are kind of unbiased. Here's a graph view of this model. So each node here is a company or asset, and all the nodes are connected. So it's a full graph. And we have to estimate all the ages for this graph. Examples would be some like a simple sample method, shrinkage method, or EWMA. And for the structure method, typically we have a linear factor model. And for the risk, it's coming from two parts, the systematic components of the factors and the idiosyncratic components. And we normally have a very strong assumption about independence between the idiosyncratic components. Here's the graph view. So the systematic component is very big and sitting in the middle, and the idiosyncratic component are relatively smaller and along the edges. Not all the nodes are connected in this graph, so we don't need to estimate a full graph. And examples would be some like a fundamental factor model, like the one from Barra, or some static model, like the one based on GeoGauge, or some mix of these two methods. And for the unstructured method, if we deal with large sets of the portfolio, then we are going to have the curse of dimensionality. If we look at the graph, it's going to be very dense. So we are going to have lots of the estimation error with this unstructured model. And for the structured model, from time to time, we are going to have some like a misspecification error. So the idiosyncratic component are much bigger compared with the systematic component. So here is the unstructured and the structured model. So now let's take a look at the conditionally structured model. The example here is a dynamic graphic model, or DGM. It starts with a very simple DOM model. You have the observation equation on the top and the evolution equation on the bottom. The interesting part for the DGM is at time t, the covariance matrix is following some like a hyper-inverse visual distribution, which is based on a graph. And we can embed some structure to the graph, and therefore the covariance matrix can have some structure. Typically, we start with an empty graph, and as more data comes in, the model will learn the underlying structure, understand the underlying structure automatically. And the nodes on the company started to connect with each other, but not every node here is connected. And here's a matrix view. So the matrix is very sparse. Typically, we can find lots of the structure in these models. And here's an example. So we built a DGM model with 100 stocks from MSCI World Index. And during the European debt crisis period, we find some interesting region effects. Here's an example. So each node here is a company, and the node size is proportional to equal risk contribution weights, and each side is proportional to the inverse correlation. So you can see in the light blue and the green dots are kind of European and UK stocks sitting in one corner. The dark blue will be the stocks from EMEA, and the orange is the Japanese stock. So this is a very strong region effect. And we also discovered some interesting sector effects during global financial crisis period. Here's the view. So the color indicates the sector here. You can see the financials and the healthcare are sitting on the top, and the IT is sitting in one corner, and all the others sitting in the rest of the corner. And on average, there is only 5% of the structures through time. And here we define these structures to be the expected number of ages from those graphs. And you can see some patterns through time for the last 12 years. And if we plot out the major events, you can see after Lehman collapse or the first Greek bailout, the structures just jumped. And then when the Europe started in the QE program, the structures started to decrease. And then early last year, when the market started to worry about China slowdown, the structures just jump again. Okay, now let's compare the forecast accuracy for different models. We built a series of covariance matrices with different models. One is the modified sample method. The second one will be the shrinkage method, which targets at a constant correlation matrix. The third one is EWMA with different decay factors for correlation and variance. And then the DGM model, the GeoGauge model, and the Barrow model. So the model on the left side is the model with less structure. And the model on the right side is the model with more structure. And here is the forecasting error bar. You can see GeoGauge model is the best, but EWMA and the DGM is also relatively good compared with others. If we look at the tracking error, so you can see in the DGM is really outperforming all the others. So today's conclusion is very simple. If you want some structuredness in your covariance model, you don't want too much or too little. You just want to be in the middle. And thank you.